I'm Ronald Cohen at the Geophysical Lab of the Carnegie Institution and at LMU Munich, and we're working on understanding properties of the deep Earth using big computer simulations of behavior of electrons. So we're starting with very small things and inferring properties of very big things. So I'll be talking about properties of the deep Earth in the lowermost mantle, and this work was done with the postdoc here, Youngjun Lin, and others. So these calculations are only made possible by using the largest supercomputers in the world. So for example, we've been doing calculations on Stampede and Titan. Titan, I think, is currently maybe the second fastest computer in the world, the fastest in the US. And we still need millions of hours on these machines in order to get results. What we do is we actually solve the interactions between all of the electrons more or less exactly, but we do it with random numbers, and I don't really have time to explain that too much, but I'll say a couple minutes about it. For example, if you wanted to find the value of pi, you could imagine throwing marbles into a circle inscribed in a square, and if you counted how many marbles fell inside the circle and how many fell out, eventually you would get an estimate of the value of pi. So that's using random numbers to solve a mathematical problem. And we're doing that to solve this problem of interactions in materials. So here's an example. We actually have real electrons moving around, and how they move around with time gives you a fluctuating energy, which we then average, and that gives us the exact energy. The problem is we need accuracy of like 9 figures before we can start doing chemistry and figuring out properties of materials. So we need extremely high accuracy. The net result, this is some older work that we did, is that we can actually calculate phase boundaries more accurately really than can be measured in experiments. And these are the kind of big simulations that are used, for example, on the Large Hadron Collider and so forth to figure out properties of high energy particles. So we're applying this to understand the deep Earth, for example, the transition between perovskite and post-perovskite in the very deep Earth. And this is kind of the final result that we would get is actually a phase diagram where these show our error bars, and we can compare this with much simpler methods, and we see we get quite a bit of difference, but still similar to more simplified methods, the kind of methods that can be done in a few hours on a computer, maybe a desktop computer compared with many millions of hours, but here we can get not only a more refined result, but we can actually get an estimate of the statistical error. And then we can apply this to the Earth. And for example, this dashed line here shows you the temperature in the Earth is a function of pressure or depth. And then this is the phase boundary, and people had been wondering about whether the temperature would pass over this phase transition twice or just once. And you can see it's consistent more or less with it passing through it twice, which is what's seen in some seismological studies.